Hi everyone, welcome back to PW English Medium channel and welcome back to UMEED NEET English series. Friends, in today's class we are going to complete electromagnetic induction, right? So as we are doing in all of the other classes of UMEED NEET English series, we are going to complete all the important topics. We are going to solve some numericals also. So today we are going to start with magnetic flux. The main important topics of today's class are going to be Faraday's laws, Lenz's laws, motional EMF, self-inductance, RLDC circuit, AC generator and transformer. Along with this, other topics like for example as induced electric field, we are going to cover those things as well, right? So without any delay, let's talk about how we are going to define magnetic flux. If you remember, you have defined what electric flux is. In a similar way, we are going to define magnetic flux also. We can define it like it is a measure of number of magnetic field lines passing through a surface, But what do we really mean by this? So let's take some example. And we all know these things. Then let's suppose that if you have got a surface like this and magnetic fields something like this. Let's suppose these are the magnetic field lines. So we know that right now maximum amount of area is linking to this magnetic field lines, to these magnetic field lines, right? Or what you can also say is that, sir, if we are to actually draw an area vector something like this, which will be perpendicular to the surface, we'll draw it. So this is going to be the area vector and this is going to be the magnetic field. So in this particular case, the angle between the area vector and the magnetic field is 0. That means when area vector and magnetic field lines are going to be 0, magnetic flux is going to be maximum. So in this case, magnetic flux is maximum. Or in some another case, you can say that let's suppose that we have got area vector as something like this and similar magnetic field lines. Now in this case, we can see that area vector is perpendicular to the magnetic field lines, isn't it? So this is your area vector and this is perpendicular to magnetic field lines. That means in this case, magnetic flux will be minimum. Here angle is 90 degree. So instead of talking these specific cases, let's draw a general diagram. And now let's say that, okay, let's suppose that we have got magnetic field line something like this. And the plane of the coil, the plane of the area is making some angle. And let's suppose something like this. This is the area we are talking about. This is the surface we are talking about. And area vector will always be perpendicular to the surface, something like this. Alright, and let's suppose this area is theta. Sorry, this angle is theta. This is area vector A. This is magnetic field B. So we can write that magnetic flux will be written as B times A into cos theta. Is that clear? So that would mean that magnetic flux is nothing but B dot A. B dot A, where magnetic flux will have an SI unit of Weber or Tesla meter square. It is a scalar quantity, right? So similar things that you have done in electric flux, no difference. Other than this, now let's move on to some questions regarding magnetic flux, because we have just started the class. Then we'll move to our further topics, right? So let's have a look at some examples. Let's suppose we have got a loop of wire which is placed in the magnetic field of 0.3 I cap Tesla. That means magnetic field is given as, magnitude is 0.3 Tesla and the direction is towards positive y axis. And the area vector is given as 2 I cap plus 5 j cap minus 3 k cap meter per second square. Sorry, just meter square, right? And then next thing is going to be for finding out the flux, simple. You are going to just write down the dot product of these two things. That means B dot A. So we have got magnetic field was only along j cap. So we'll just multiply it with j cap. Everything else will be 0. That means the flux will come out to be 1.5, 0.3 times 5 is 1.5 Weber. That's it. Very easy question, I know. Let's move on to some different questions. Now pause the video and think about the answer. What's going to be the answer? I want you to pause it and I want you to think about the answer. What's going to be the flux passing through this area, right? Now, this is where you'll have to actually calmly read the question and identify what is the angle between magnetic field and area, right? The answer for this question is going to be 0. There will be no magnetic flux linked with this. Why? The reason is that these magnetic field lines lie on the plane of the loop, or whatever this is, on the area, right? So that means the angle between these two things is actually 90 degree. What two things? The angle between area vector and magnetic field lines, right? So please suppose it's something like this. Let's suppose this is the loop, alright, this is square, assume it to be a circular area. Magnetic field lines are like this on the loop, right? So area vector would be something like this, and then magnetic field is like this. So angle between area vector and magnetic field lines is 90 degree. So there will be no flux linkage for this part, right? So easy questions, not to worry about. Magnetic flux is not that difficult, and we are going to talk about magnetic flux later on also. The whole chapter is there for finding what magnetic flux is going to be. So not an issue, right? So I think I can move on to the chapter, and the chapter is actually related with Faraday's experiment. There is Faraday law, but first let's talk about how actually Faraday got, how he actually invented that law. Not invented, but how he discovered that law, right? For this law, he actually did some experiment, and I'm breaking down that experiment, not stating that the experiment word by word, right? So you'll have to actually catch the concept and the feeling of this experiment. What do we have over here? We have a solenoid in which we do not have any current carrying source, right? So we don't have any battery, nothing like that. We just have a galvanometer, we have got a solenoid, and we have got a bar magnet. We know that a bar magnet will produce magnetic field. From this north pole, magnetic field lines are going to be created, something like this. Let's suppose this is at center, magnetic lines are something like this, and from the center only the magnetic field lines are going to move something like this, and from these points they will, that's how the magnetic lines of force will behave. Right? So right now what we are doing is, or what Faraday did was, when he actually made this, when he set these two solenoid and the galvanometer and the bar magnet into relative motion. So relative motion basically means, let's say that right now this is at rest and this is in motion. This is moving with some velocity v, right? This is one of the case. So what he observed, that when there is a relative motion between bar magnet and solenoid, there is a deflection in the galvanometer, right? Which was actually quite amusing, quite surprising for him and for everyone at that time, because by that time we knew that, okay, current, we can create current with current carrying sources, that's not a problem. But right now we don't have any current carrying source. All we have is actually a bar magnet and a solenoid, and when we move these two, when we actually move them in such a way that there is a relative motion in between them, there is a deflection in galvanometer, right? So the first part over here was when there is relative motion, between bar magnet and solenoid, there is deflection in galvanometer. See, we are not jumping into what that current is. That current will be called as induced current or anything like that. We are not jumping. Let's first try to understand the experiment, then we'll talk about the law and then we'll start solving some questions. Okay? So that was the thing. Now in the next experiment, I mean similarly in the same experiment, not next, but in similar experiment, he did it another way. Now he actually said that when we actually move this bar magnet, away from the solenoid, that means in opposite direction. In this case, galvanometer or galvanometer's deflection was in opposite direction, Alright, so okay, so enough of these experiments. You can now do it. I mean, you can study quite a lot of variations from here. Like for example, as now bar magnet is at rest, solenoid is moving, and so on. But we are not going there. 2 experiments are sufficient for us, right? So the thing is, now we can formulate what Faraday actually, what he would have thought of it, right? Of this experiment. See, when there is relative motion between bar magnet and galvanometer, what we can actually say? We can say that initially there was some flux linking with this solenoid, this area. There was some flux linkage, right? And when there will be a relative motion between a bar magnet and a solenoid, this flux linkage will change. Are you getting it? And of course, you can say in this case, sir, basically the thing that is right now changing is the magnetic field intensity, because when this bar magnet was closer to this, when this solenoid was closer over here, at this point magnetic field was stronger, right? And as soon as it's going to move away from the bar magnet, the magnetic field intensity will go down. So magnetic flux will decrease. But right now we are saying that if at all magnetic flux will change, Faraday said that as soon as the magnetic flux changes, there is an induced current in the coil, or there is an induced current in the conductor or in the solenoid, whatever you want to call it, right? So basically he said, in the experiment he said that if there is, now I'm actually trying to write these things, try to write the law in short form. Just a second. So basically what he said, that if there is a change in magnetic flux, this will lead to an induced current. An induced current will be produced. And if we have got induced current, we can also talk about induced EMF, right? So when we are saying induced current, we can also say induced EMF, right? Or induced voltage, induced potential difference will be produced in the coil or conductor. You can just write in the coil. Alright, so hopefully everything is clear till this point. This was the, what we can say, this was the result of Faraday's experiment. Then we are going to also talk about Lenz's law. Now he actually discovered that, and all of these things we are going to write it in the Faraday's law. He discovered that induced EMF is actually directly proportional to the rate of change in magnetic flux. So that means if let's suppose magnetic flux is changing, so it means that there will be induced current, and if there is induced current, there will be induced EMF. Fine. But there is one more thing. If induced EMF is changing with greater rate, then there will be more EMF. That is the point. So we are not just concerned about the change in magnetic flux, we are concerned by rate of change in magnetic flux, right? And it will be good for us that we'll write a negative sign also over here. This negative sign we'll understand it by Lenz's law, but for now let's write it a negative sign, okay? So that means we can rewrite this thing as E is directly proportional to minus d phi by dt. So this will be the formula for instantaneous induced EMF, and the proportionality constant comes out to be 1. So this will be minus d phi by dt. So this is an instantaneous EMF. Now we can again rewrite all of these equations in different ways. One is surely going to be average, but before that, let's suppose that if there are n number of turns, if there are n turns in the loop, if there are n turns in the loop. So if there are n turns in the loop, what we are going to say is that now the total flux will become n phi. So that means now the induced EMF will become minus n d phi by dt. N d phi by dt. Alright, or if you are going to talk about an average EMF, then average EMF can be written as minus n del phi by del t. Hopefully everything is clear, right? So this means that if let's suppose we are saying that we have got, and this is just one example, we have got a loop over here, and this loop has got resistance R, and let's suppose this magnetic field intensity is increasing. It is time dependent, and this magnetic field intensity is increasing with time, right? So by the way, I can directly tell you that the direction of induced current will be something like this. I'll explain the Lenz's law, but for now, I just want you to go step by step. So first now we have discussed what Faraday's law is. Faraday law can be written something like this. We'll again discuss about Faraday law, what do you mean by phi, everything will be discussed, but for now, let's suppose we have got a loop. And let's suppose magnetic field is increasing. So magnetic field is increasing, so that means phi will change. Magnetic flux is BA cos theta. So if magnetic field intensity is changing, that means B is changing, that means phi is changing. So if phi is changing, that means there will be an induced EMF. That induced EMF will be written something like this, because there is only one turn, so I can use this formula minus d phi by dt. But if I want to write down the current, what I'll do is I'll assume there is a fictitious battery. Well, there is no battery, but I'll assume there is a fictitious battery, something like this, which has got EMF E, and this current will be written as the magnitude of E divided by resistance. So that's it. So that means we can rewrite this thing as 1 upon R d phi by dt. Right? So till now we have, I actually owe you explanation of this a negative sign, that is Lenz's law. And second is, let's talk more about this phi. Let's talk more about how can actually, what are the different ways in which we can change the magnetic flux, right? Let's talk about one by one of each of those things. Now when we say that, sir, induced EMF is actually equals to minus n d phi by dt, what we really mean is, we can again rewrite this thing as, this thing can be written as minus n d ba cos theta by dt. Okay. So if you want to change flux, think about it. If you want to change flux, in how many different ways you can change it? This is BA cos theta. So now one of the ways can be that we can actually change magnetic field. So dB by dt is there, and it could be anything. It could be a usually they usually give this thing as a constant. So dB by dt is there, right? So dB by dt is changing. So this is the rate of change, or you can write this thing as some constant k, and other things like area and theta are constant. Right? Or what you can say is that, sir, let's suppose area is changing, there is some dA by dt which is some constant, and magnetic field and theta is actually constant, they are not changing. By the way, what is this theta? Of course, angle between magnetic field and area, right? Another thing is, let's suppose there is a change in theta, and if there is change in theta, magnetic field will be constant, right? And the area of the loop is also constant, by the way. Area is also not changing. All right. Now, out of all of these things, there is also one more point to be noted. This thing is actually known as motional EMF or dynamic EMI, motional electromagnetic induction, and this thing is known as static. And this thing is also known as static, right? So till now we have seen that if we want to change magnetic flux, either we can do this, or either we can do this, or any combination of this is also possible. But in NEET, generally they are not going to ask you a case in which multiple things are changing. So you don't have to worry about that, right? So we'll discuss each case of these things, then only we can understand what we really mean by changing dA. So we are going to discuss each and every case, so not to worry about this as well. Okay? Right now, if you are thinking, sir, I'm not really getting how this will happen, how that will happen, so hang on, then we'll again come back to this. So for now, before completing Faraday's law, it would be really necessary to understand the Lenz's law, right? It would be really important to first understand what Lenz said in his law. Now this is the law. First of all, this is a law for direction of induced current, Alright, mainly we are going to use this law for this thing. Now what does this law says? This law basically says, according to this law, the direction of induced current, will be in such a way that it will oppose the cause which has created it. Quite a dramatic definition, right? But I'll explain it. What does this mean? I'll explain what does this definition means, and using our old experiment example. This was the experiment, na? So from Faraday we got to know, sir, if there is relative motion, basically magnetic flux is changing. Now can you tell me which case is this? What is happening? What thing is changing over here? Here dB by dt is changing, right? Area is not changing, angle is not changing. Here dB by dt is changing. Okay. So the thing is, according to Lenz's law, Faraday got us till here that okay, there will be induced current, fine. But in which direction that induced current will flow? We know that there is some deflection in galvanometer, but without looking at the galvanometer, how can I find out what is going to be the direction of current over here? So the thing is, induced current wants only one thing. Induced current does not want magnetic flux to change. It wants, there is a term in English which says that status quo, right? So it wants to maintain the status quo. That means it wants to maintain the situation as it was before. Now think about it. Initially, there was no relative motion. Initially, there was no relative motion. Let's suppose initially this whole of these things was at rest. Done? Now you have decided, sir, now we are going to change this situation. Now we are going to move this bar magnet towards this solenoid. So this is the change. That means change is definitely magnetic flux is increasing. Definitely the change is that the magnetic flux is increasing, and this is increasing because of greater intensity of magnetic field lines are now crossing it. But what is the main cause of it? The main cause is that we have given some velocity to this bar magnet. So what will induced current will do? Induced current will not want this bar magnet to come close. So it will try to flow in such a direction that there will be a north pole. Because of this induced current, this solenoid will also create its own magnetic field, something like this. Right? And this, on this side, there will be a north pole appearing because of induced current, which will try to oppose this bar magnet. Alright, are you getting it? So the solenoid does not want, the induced current does not want the bar magnet to come close. Why? Because of that magnetic flux was increasing. And to maintain that status quo, it will try to repel it. So that's why we'll have a north pole. And please don't ask me, sir, how you found out the direction that, right? Do you remember clock face rule? We have talked about all of this thing in magnetism and moving charges and magnetism, right? Another example, dosto. Let's suppose initially this both of them were at rest. So this is the status quo. This was the original situation. Now you decided that, let's say, sir, now we are giving this bar magnet some velocity. So now because of this, magnetic flux will now decrease. And because magnetic flux is decreasing, why? Because now magnetic field intensity is getting weaker and weaker. So what would induced current will do? It will actually flow in such a direction that there will be south pole in this direction, which will attract this bar magnet. Why? Because please remember, it is not to oppose the motion, it is actually to oppose the change in magnetic flux. Because it is moving away, it will try to attract it. If it was moving closer, it will try to repel. Right? It always changes it always opposes the change, right? So that's why we have got this negative sign, and then let's talk about some more cases, right? Like for example, as this one. Now I want you to pause this video right now and solve it by yourself. Good. Come on. Let's quickly solve it. Quick, dosto. What do we have over here? We have got a figure shows a long current carrying wire and two rectangular loops moving with velocity v. Find the direction of each loop. Find the direction of induced current in each loop. They want us to find out the direction of induced current in each loop. Let's talk about loop 1 first. In loop 1, magnetic flux is something like this. This is the magnetic flux. And this, by the way, this thing is actually moving something like this. After some time, it will be somewhere over here. And there is also a wire, there is infinite wire. So now you tell me, dosto, I mean, surely you can say, sir, see, the problem is that, right, first of all, I'll tell you what answer is. In the first case, there will be no induced current. In the first case, there is no induced current. Why? Because there is no change in flux. No induced current. The reason is that d phi by dt is 0. There is no change in magnetic flux. Now somebody might say that, sir, but why it is moving? But the thing is that if you are going to actually closely see, at this point also, each and every point has same magnetic field and area. Are you getting it? So that total flux, now I don't want you to find out the total flux, we'll have to integrate it to find it out, because magnetic field will be different at each of the points in the horizontal direction. But still, I can still say that, sir, at this point also magnetic flux is same, phi 1. I've got no problem, fine. Because the thing is, if you are going to talk about an current carrying an infinite current carrying wire, magnetic field is given as mu naught I upon 2 pi r. Upon 2 pi r. This is the formula. That means magnetic field is actually inversely proportional to r. So if the loop is moving parallelly to the wire, to the length of the wire, the magnetic flux will not change. Whereas in the second one, you can see that as it is going away from the wire, in the second case, excuse me, in the second case we can say that magnetic field is decreasing as loop is moving away. As loop is moving away. Right? Okay. Now second thing, what is the direction of induced current? Because what is the direction of the magnetic field? Current is moving like this. Direction of magnetic field cross. So that means all over magnetic field is cross everywhere. So the reason for change in magnetic flux is that magnetic field is decreasing. So what would induced current want? Induced current would not want this magnetic field to decrease. So it will support it. This is where many students face a trouble. They'll think, sir, but sir, you said that induced current should always oppose it. Sorry, I've got a little cough. I never said that induced current will always oppose the magnetic field. I said induced current will be in such a way that it will oppose the reason that has produced it. The reason was that magnetic field is decreasing. So opposing this reason would mean that induced current will support this magnetic field. Are you getting it? So that means induced current will be in clockwise direction. Think about it, dosto. If induced current moves in clockwise direction, Because of this induced current also the magnetic field will be inwards, which will try to oppose the change. Hopefully everything is clear. Quickly let me know in the comment section if you have got this. Now let's move on to next question. Next question says figure shows a coil placed in a decreasing magnetic field. So that means we have got dB by dt as negative value. The magnetic field is decreasing at a rate of 10 Tesla per second. Find out the current and find out the current in magnitude and direction, right? So first of all, induced EMF will be minus d phi by dt, because there is only one loop, and over here also we will say that minus a dB by dt. Now please understand each and everything. Although the flux is written as BA cos theta, over here we can see that the angle between area vector and magnetic field is 0. So cos 0 will be 1, and out of B and A is a constant. So that means minus a dB by dt. So this will be minus the magnitude of E will be just a second, sorry. Yeah, magnitude of E will be area A, that was 2 meters square, times dB by dt. dB by dt is given as 10. That means this is going to be 20 volt. And induced current will be 20 volt divided by resistance. That means 5, which is going to give you an answer as 4 ampere. Right? Now what is going to be the direction of induced current? Now again, magnetic field is into the plane, right? Magnetic field is coming out of the plane. That is, it is dot and it is decreasing. So induced current will be in such a way that the magnetic field due to induced current will try to support this, right? Because it does not want it to decrease. So it will try to support it. So induced current will flow in anti-clockwise direction, something like this. Hopefully everything is clear till this point. Please check quickly. Next question. The magnetic flux in a closed circuit of resistance 20 ohm varies with time t according to the equation. This is I think 7t square. है ना? This is I think the correct form would be phi equals to 7t square minus 4t. The magnitude of the induced current at t equals to 0.25 is, right? Okay, let me now check, because I think if this is the case, the magnitude of this thing, right? See, if this is the d phi by dt would be 14t minus 4, right? So if they are talking about magnitude of induced current, that will be mod E divided by R. So E is nothing but 14t minus 4 divided by R is resistance is given as 20. And they are asking at t equals to 1 by 4. That means 0.25. Now we'll have to actually check whether this equation is correct or not. So 0.25 minus 4 divided by 20. Let's check whether whether we are finding anything from the option or not. So yes, and by the way, this is again, please take the magnitude only. So the correct answer is actually coming out to be 0.025 or 25 milliamperes. So A option is correct. Done. Hopefully everything is clear till this point. Now let's talk about something that is called as motional EMF, right? We actually discussed this term in a short way when we were talking about change of magnetic flux, but now let's discuss it in detail. Let's suppose we have got a frame over here. On this frame, we have attached a moving rod. So a rod can be moved into this plane, right? and magnetic field is into the plane. Let's suppose magnetic field is B and it is constant. Now we are not talking about change in magnetic field. Can you please sense that just now we have completed one of the case when we were talking about dB by dt, right? Now let's say this rod has got certain velocity and this velocity is in this direction. What will happen because of this? So because of this flux link, this is the flux linkage, this will change. Right now, let's suppose this length is actually x. From here till here, this length is actually, let's suppose, x. Right? And the length of this rod is, let's suppose, it is L. Length of this rod is, let's suppose, L. So right now the area is L into x. Now if it will, let's suppose if it moves with dx displacement, if this rod moves with a dx displacement, there will be a change in magnetic flux, isn't it? There will be a change in magnetic flux, and that change in magnetic flux will be E equals to minus d phi by dt. It will be in accordance with Faraday's law, of course. And now we can say that, okay sir, that means that this will be written as, at that particular point, this is actually dB and dB into area, dBA by dt, and instead of area, can I directly write L times x times dt? Now you please tell me, is magnetic field changing? No. Is the length of the rod is changing? No. So I can take out these things outside. So I'll be left with minus BL times dx by dt. And what is dx by dt? Dx by dt is x is this. Rate of change in x with respect to time t is nothing but velocity, isn't it? So that means we can rewrite induced EMF as minus BLV. Minus sign is just telling you the direction of induced EMF. That we'll talk about it just now. But hopefully everything is clear till this point, right? What I'll do is I'll try to make a copy of this. So this was the case. That means induced motional EMF for a moving rod is BLV, where B is magnetic field, L is the length of the rod, and V is the velocity with which it is moving. By the way, very important, if you have got, if in another case, let's suppose you have got magnetic field like this, and you have got a rod which is not actually moving, which is moving with some angle, right? So let's say this is the velocity V. What you need to do is, you need to actually find out this length. This is going to be L sine theta, right? So you can do it like that. Now next thing is finding out the mechanism of this thing and the direction of induced EMF. So we have already written it. Induced EMF comes out to be, E comes out to be, magnitude is BLV. Great. Now let's talk about it over here again. What would be the direction of induced current? Okay, there are two ways to understand it. First way is, we have got a rod which is moving something like this, and there will be a current in this rod. Fine, that current will be an induced current, correct? This will create an induced current in the rod. Induced current in the rod. Acha, please understand, induced current in the rod, and this rod is kept in the magnetic field. Do you remember something as magnetic force? Magnetic force acts on a current carrying conductor kept in magnetic field. Do you remember this concept? So according to this concept, if we have got a current carrying conductor kept in magnetic field, there will be a force on it. Acha, you tell me, magnetic flux is increasing, right? So what would induced current want? Induced current would want that, sir, magnetic flux should not increase. So induced current would want that, sir, there must be a resistive force acting on this rod and that must act in this direction. Is it clear? There must be a resistive force, there must be an deacceleration produced on this rod due to induced current. That's what the induced current will want. So that means there must be a force which will act in this direction, and this will we can find it out using this Fleming's left hand rule. Magnetic field is something like this. Force is acting in this direction, so that means current should move from top to bottom. Is that clear? So direction of current will be, direction of current is going to be something like this. This is going to be the direction of current, I. So that means if you want to actually draw a fictitious battery, you will draw it something like this. That is, the induced EMF is going to be BLV. If you haven't got it, you have the luxury of pausing the video, rewinding it, and please again see what I am trying to say. Okay, got it? I am explaining you it in a different way. That is, you are going to find this thing in many books as mechanism of induced or of motional EMF. This is also very interesting. This is mechanism of induced motional EMF. I could have simply written motional EMF, but it's fine. Now think about it. We have got a rod. I'm just drawing the rod. I'm not drawing the whole of frame. I've got a rod kept in magnetic field. Fine. Let's talk about a positive charge in the rod. I know there are no free positive charges, as we have got negative charges, but for an hypothetical situation, let's say till now we know that, okay sir, this rod is actually moving in this direction. This rod is moving in this direction. So let's suppose that it will have many charges. Let's say that it has got one positive charge also. So a positive charge we have got over here. A positive charge is moving in this direction. And magnetic field is into the plane. Now please understand. Magnetic field is into the plane. Positive charge is moving in this direction. The force on positive charge will act in upward direction. Is it fine? That means in reality you would now say, sir, a rod has got no positive charge. So I will say no worries. This means that it has got electrons. Those electrons will start to accumulate on the bottom side of this rod, which will leave the positive ions on the top side of the rod. This will be because of magnetic force. So on an electron, magnetic force acts in the downward direction. This is the magnetic force we are talking about, which is nothing but QV cross B. This magnetic force is going to be actually the same force which is used in, which we talk about in batteries. This is the driving force. It is actually making the charges move away from each other. It is actually separating the charges, and that's why we always talk about EMF in this electromagnetic induction chapter. Have you ever noticed we never talk about EMF in capacitor or EMF across resistor? We always say there is a potential difference across capacitor, there is a potential difference across resistor. But over here we are saying that there is just not potential difference, there is also an EMF build over here. Why? Because this magnetic force is actually creating the separation between charges, right? And as soon as it's going to separate the charges, we have got some positive charges on the top, some negative charges on the bottom. There will be also an electric field produced. That electric field will be from positive charge to negative charge. There will also be an electric field produced. And as the magnetic force will keep on separating the charges, this electric field will also increase in magnitude. Now think about a situation. We have got an electron, on it a magnetic force is acting in downward direction, and similarly an electrostatics force will act in the upward direction, isn't it? Because of electric field. Hopefully you can see that color. At a certain point, or I should say after some point, this magnetic force and electrostatics force becomes equal. Obviously they are acting in opposite direction, but at a certain point they become equal, and at that point we say that EMF has been established. Induced EMF, I should say induced EMF has been established. Right? Hopefully everything is clear with this concept. I have explained all the things, why magnetic force will act in that direction. Why magnetic force will act in that direction? Because it will try to resist the motion. Now after this, there is one specific case for motional EMF, that is rotational EMF. Let's suppose that you have got a similar rod, but only now it's actually, instead of moving in translational motion, it is actually rotating. So let's suppose you have got a rod, something like this, and it is rotating with some angular velocity omega, right? So there will be an induced EMF in this also. For this one we will say that, okay, let's suppose that at an x distance we have got an element of dx length at a distance of x. So this part will have a velocity of x omega. So this will have a small EMF of dE, and that will be bv times length, bvl, right? So we'll integrate it to find out the entire EMF, the total net EMF of the entire rod from 0 to L. So that will be E equals to b omega L square by 2. Very easy thing, not so difficult. That's it. You need to remember these things, right? B omega L square by 2. That is what is your rotational EMF. Done. Hopefully everything is clear with this concept also. You don't have any doubt with this one. Now please let's also look for some example, then we'll move on. The current flows in a circuit as shown below. If a second circuit is brought near the first circuit, okay, then the current in the solenoid circuit will be, first of all, you have got a battery like this. That means the current will flow in this direction. Is that correct? Which means that current will start to flow from something like this. Which basically means, according to our clock face rule, over here we have got north pole, over here we have got south pole. And if this is moving towards this one, this will have a current something like in such a way that it will appear to have north pole over here as well. So the direction should be something like this. Sorry. This is going to be actually south pole. This is going to be south pole, so this is also going to be south pole, isn't it? This one is north pole. This one is north pole. So this one is going to be south pole, right? So if this one is going to be south pole, this should be also south pole, so that they can repel. And for that, the induced current should be something like this, right? So basically, if you are talking about, they are saying that he from the observer, right? So it is south pole. So from the observer, the direction of current is something like this. That means anti-clockwise, right? Also, you can do all of those things also that you might have seen, that for south pole, they do something like this, right? No, this is for clockwise. Is it? Just a second. Let me first check it again. So this is definitely, this is going to be actually, this should be something like this. So this one is anti-clockwise. Yeah, this is going to be anti-clockwise, no doubt about it. And that law, that thing is also correct, by the way, because for that's going to be north pole, na? This is south pole, so that will be north pole, so that will be anti-clockwise. That thing is also correct, that you might have seen that pattern, right? So now let's move to the next question. The current flows from A to B as shown in the figure. We have to find out the direction of the induced current in the loop. All right. So current flows like this, and we have to find out the direction. So okay, let's do it. What would be it? The current is not changing. The current is actually not changing. So if current is constant, that means magnetic field is going to not change. So it should be none of these. If current is constant, then there will be no induced EMF. Chaliye, moving on. Now let's see this one. Consider a metal ring kept on a horizontal plane. A bar magnet is held above the ring with its length along the axis of the ring. If the magnet is dropped freely, the acceleration of the falling magnet is a very typical type of a problem. See, usually the magnet will fall with an acceleration of, when there is no ring, it would have fallen with an acceleration of g, right? But because now the thing is that there is magnetic flux linking with this ring, and continuously that this magnetic flux is changing. So there will be an induced current in the ring, and because of this induced current, there will be a magnetic field also, which will try to oppose this magnet, right? Which will try to oppose this magnet with certain acceleration. So this will be actually less than g. By the way, one quick tip. If they'll ask you that it has actually passed now, from the ring, the bar magnet has passed. Now tell me what's going to be the acceleration of this bar magnet. Now sometimes what students do is, they sometimes say that, okay, now sir, the acceleration will be greater than g. This is wrong. Still it will be less than g, right? Because now it will try to actually attract it. Similar concept that we have seen in Faraday's experiment. So if you have doubt, pause the video, check again, right? Now after this was also a good problem. After this, I want to actually look, till now we have studied when dB by dt changes, that is when magnetic field changes. We have studied when dA by dt is there, that means when area is changing. Now let's consider when theta is changing, right? So let's take one example. Let's suppose that we have got, in this region, we have got magnetic field something like this. In this region, we have got magnetic field as cross. Right, and we have got a semicircular object over here, and this semicircular object is actually something like this. So I'll do one thing. This is a semicircular ring, alright, and it is actually revolving about this diameter. About this point. With angular velocity omega. Right? So that means after some time this will happen. After some times the thing that will happen is, let's say it has actually shifted by certain angle, it has been rotated by certain angle, something like this. this is after time t. So this much amount of area has been, this much amount of flux has been linked, isn't it? Right now there was no flux, it is moving with some angular velocity omega. Now there is some flux at time t, so this is actually at t equals to t, and this was at t equals to 0, right? Got it? First of all, let's find out at any time what this area is going to be. Don't mind, okay, let me do one thing. I am writing it over here. What is the area? That is area that is inside. So that will be 1 upon 2. Let's say radius of this thing is r. 1 upon 2 r times, let's say this angle is, by the way, this angle is going to be theta, right? So this will be r times theta. So we can rewrite this thing as 1 upon r square, and theta can be written as omega t. So induced EMF will be minus d phi by dt, and instead of phi we are going to write minus b dA. So instead of area, see, whatever thing is constant, first of all let me write everything over here. So this will be 1 upon r square omega t by dt. So induced EMF will finally come out to be minus 1 upon 2, and this will be b omega r square. So this is the final answer. So this is your another case is also completed, right? When angle is changing, when theta is changing, d theta by dt is nothing but d omega by dt is nothing but d theta by dt is nothing but omega. Okay, so now after this let's move on. Now let's talk about induced electric field. Although we have not, I don't think that generally NTA asks from induced electric field, but still it is one of the topic. Let's complete it. Let's quickly complete it. Although it's quite a good topic. What do we really mean by induced electric field? Till now we were discussing. We were saying that, sir, if there is changing magnetic field, or changing flux, there will be an induced current, right? And we got to know about the motional EMF. We really understood how motional EMF worked, because we understood the mechanism of motional EMF. But let's suppose we have got a region over here which has got some magnetic field, something like this, and we have got a loop over here. And let's suppose this magnetic field is increasing with time. So if magnetic field is increasing, there will be an induced current, something like this. That means at any point, if I am going to talk about an electron, it will move in opposite direction. This will be the velocity of electron at any point. My question is, who is making this electron move? There is no one. Because when we were talking about motional EMF, think about it, when we were discussing motional EMF, the driving force was magnetic force. Because of magnetic force, first they got separated, and then we said that, okay, after getting separated, now electric field is there, now EMF is established. But for this particular example, let's not talk about induced electric field for now. Let's just say that, okay, everyone knows this example. We have just studied it, that if you have got magnetic field inside of it and that magnetic field is increasing, so induced current will actually try to make its own magnetic field that will actually oppose this increase. So it will be in the direction of anti-clockwise, right? So that thumb comes out, magnetic field comes out. So what is making these electrons move at the first place? The answer is induced electric field, right? To get the feel of this particular thing is a little difficult, but that's how it is, right? Induced electric field is actually produced when we have got change in magnetic field. This is what we are going to say, right? So over here, even if there is no loop, if magnetic field is changing, there is induced electric field, even if there is no loop, right? So now we are going to say, let's rewrite, first let's write the definition that induced electric field is produced, induced electric field is produced due to changing magnetic field, due to changing magnetic field. Acha, these electric field lines are a little different. These are not your normal electric field lines. These are closed continuous loops. These are closed continuous loops. This is a difference with a normal electric field lines, that is induced electric field lines. These are closed continuous loops. That means if you are going to talk about electric field at this particular point, again the thing is same, magnetic field is actually increasing. If you are going to talk about induced electric field in these cases, I am going to say that those are going to be something like this. Concentric, of course, something like this. These are your induced electric field lines. Alright, and the direction is obviously going to be in the they will be in, along the direction of that current. So this is going to be the direction of E. Right, now because these are closed continuous loop, one more very important thing, if you will write down the integral of E dot dl, that will come out to be 0 now, because dl, if we are talking about a closed loop, dl will be 0. So E dot dl will be actually 0. E is same at any given point. Let's suppose you want to find out from the center, you want to find out electric field intensity at any point. Let's suppose at this point you want to find out. Now wherever you're going to make a point at this particular, at this distance, electric field intensity will remain same. Right? Electric field intensity remains same. So the integral of dl, this dl vector will be 0 for a closed loop. Right? So now this is very important, and this is the case. If this is the case, there is another difference, that this is actually a non-conservative field. This is a non-conservative field. That means if you are going to, that means the work done to move a charged particle between 2 points is not path independent, it is path dependent, right? And you can also understand it in a way that, let's suppose that this was the loop, right? Initially this was the loop, and let's say that I have got a battery, fictitious battery over here, which has got EMF of 2 volt. Now if I'll move one charge in one loop, the total amount of work that will be done is 2 joule. If I'll again move it, now the total work will become 4 joule, right? Which is actually, which basically means that work is again and again increasing, which is not something that you have learnt in conservative forces. Are you getting it? So it is a non-conservative force, so we are not going to talk about potential energy. So no potential energy over here. Potential energy is a concept which is related with conservative fields. We are not going to talk about any potential energy at these point, right? Although what we can actually do is, we can find out the formula of induced electric field again using our normal rules, right? There is just one big change. This is actually not equals to 0, and I'll tell you why. The thing is that this is actually integral of E dot dl. The integral of E dot dl is 0 for conservative. Sorry, my bad. It is 0 for conservative, and we can understand it. Let's suppose that between 2 points, a charge is moved from, or any conservative, you don't have to think about the charge. Let's suppose that you move a block from A point to another point, you do a work of W1. When you move the block from top to again to the bottom point, the net work is going to be minus W1. The net work done is going to be 0. That is not possible over here. That's what I was saying, that if you move a charge, the work done will be EMF, let's say 2 volt. Then if you'll again move the charge, it will be again 2 volt. So it will become 4 volt. So that is not possible for a non-conservative field. So E dot dl is not equals to 0. This means that E dot dl is nothing but induced EMF, right? This integral, this surface integral of E dot dl is nothing but, sorry, the line integral E dot dl is nothing but your induced voltage or induced EMF. So if this is the case, we can write that E dot dl can be written as minus d phi by dt. That's it. And then we can talk about all the other cases over here as well. So for example, you have got magnetic field over here. And let's suppose we have got a loop, something like this. And let's do one thing. Let's say magnetic field is inside of this thing. And magnitude of magnetic field is increasing. So some dB by dt is there, and that is some constant. And you want to find out the induced electric field at 3 different points. One is somewhere inside. That means at some point R, at some another point outside, and that will also cover that thing. Let's say this is RO, that is RI. Right? You want to find out the induced electric field, not magnetic field, induced electric field at these 2 points. So now what we'll do is, we'll use the same thing. So for an inside point, we would say that E dot dl, that means E times 2 pi R I is equals to minus d phi by dt. And now let's talk about just the magnitude. So area of what? When we are going to talk about the flux, now we'll actually make one thing over here. We'll make one surface like this. This is the area that we are talking about. Right? So we are going to write area out from here, that is pi Ri square times dB by dt. Isn't it? Because this flux is nothing but, this is actually dBA cos theta. Cos theta is 1 by dt, and d area is constant, so we have taken out it outside. So electric field will be, pi can also get cancelled out, Ri by 2 multiplied by dB by dt. This means that electric field is directly proportional to R till you reach the surface, right? Second, let's discuss outside point, and simultaneously we can also talk about a point on the surface. So outside point. So for outside point, if you are going to draw a surface, something like this. So we'll write E into 2 pi Rho equals to area. Area is of magnetic flux. Now area can be maximum. Let's suppose the radius is capital R. So that would be pi R square dB by dt. So that means you will get E as, pi can get cancelled out, R square upon 2R naught dB by dt. So from here also you will get E is actually inversely proportional to R. Alright, so this was all about induced electric field, right? We have talked about motional EMF as well. Now let's talk about self-inductance. See, what is now self-inductance? Self-inductance is actually a property of a wire. So every wire has this property which opposes the current. According to this property, wire opposes change in its own current, that is self-inductance, right? And so this means that, let's suppose you have got a wire something like this, and in this wire current I is flowing and this I is changing. Let's suppose it is increasing. So a fictitious battery is going to be produced over here. Which will try to reduce this increase in current. And this fictitious battery's EMF will be again governed by the same laws, right? Hopefully everything is clear. Now you can actually understand this concept with detail if we are going to talk about a solenoid. Let's suppose we have got a solenoid. Why do wires or why do conductors do these kinds of things? Let's suppose we have got a solenoid, and in this solenoid you have got some wires wound up. And if we are going to change this current I, the magnetic flux that is linking with this coil will also change, right? The magnetic flux that is linking with this thing will also change. That means with this particular area, this is going to change. So if this is going to change, there will be an induced current which will try to reduce this change. So for the case of what we can say of a solenoid, we know that flux can be written as B into A, and B can be written as mu naught times Ni into A, right? So that means for any type of flux, we can say, if we are talking about self-inductance, flux is directly proportional to the current. So we'll remove a proportionality sign, we'll try to write a constant. That this constant is known as coefficient of self-inductance, phi by I, coefficient of self-inductance. And if we have got a solenoid of length, let's say of length L, of number of turns per unit length as small n, so we'll simply say that for this particular, this is the phi, right? This is the phi. So phi upon I would mean mu naught n into A. Now there is one more thing. This flux was for one single turn, isn't it? Now if I'll multiply with capital N, that will be total flux. So this will be total flux. Capital N. So L will come out to be mu naught. If I'll write this instead of this N also, or this N also, I'll write, I can write small n. So small n square, or either ways, whatever you want to write it, right? You can write this thing something like this also, A upon length. Let's say length is, let's say this is length. I am writing length something like this so that you don't get confused. So now what you are seeing is that self-inductance, coefficient of self-inductance depends upon medium, it depends upon area, and it inversely depends upon the length. That means it depends upon the geometry and it depends upon the medium. These are the two things on which it depends, if we are going to talk about self-inductance, right? Hopefully everything is clear till this point. So this means that whenever you are going to talk about any wire, let's suppose you have got any wire. Till now we used to say that okay, every wire has got resistance. From now on we are going to say that every wire has got resistance as well as it has got some inductance. So it has got some resistance and inductance will be drawn something like this. This is the symbol for inductance, right? So for inductance till now we have got one formula that L can be written as phi upon I. It is a scalar quantity, we have got it. The SI unit of L is going to be Henry or Weber per ampere, right? Now what this thing will do is, let's suppose that current I is flowing like this and current I is increasing in magnitude. There is some di by dt. So we can rewrite this circuit as, we can rewrite this wire as resistance R, and then over here you will have that fictitious battery that we were talking about. And how we are going to write it? See, instead of phi you can rewrite this thing as Li, and you used to write E equals to minus N d phi by dt. So which means that E can be written as minus N, instead of phi, L is a constant, so I will write L di by dt. So this is your new formula for induced EMF in terms of coefficient of self-inductance. This is known as coefficient of self-inductance. So because current was increasing, what would inductor want? Inductor would want that current should not increase. So a fictitious battery will be over here, something like this. And the magnitude of the EMF of this is going to be L di by dt. Right? In another case, let's suppose that current is decreasing, so the polarity will get reversed. It will try to increase that current. It does not opposes the current, it opposes the rate of change in current, right? So for this particular thing, let's have a look at one example that I have got over here. That is something like this. We have got three questions clubbed in one. AB is part of a circuit. Find the potential difference between point A and B. Find the potential difference between point A and B. Okay. If current is 2 ampere and it is constant. So if current is 2 ampere and it is constant, it means that di by dt is 0. So there will be no induced EMF because of inductor. So this is of no use. Use a normal wire over here. So we'll write for the first question, we'll write something like VA, then we'll move on. We move from positive terminal of the battery to negative terminal. So as you know, if you have any trouble in these sign convention, watch my current electricity video also. So we'll write, because we are moving from positive to negative, we'll write minus 5. Then we have got a resistor. Across resistor always we write as potential drop. If we move along current is actually 2 ampere, so 2 times 2 is 4 and equals to, whenever we got to another point we write it on the other side. So that means VA minus VB is 9 volt. So for the first one the answer is 9 volt. Alright. Now let's talk about second case. When current is decreasing and current is decreasing increasing at a rate of 1 ampere per second. So I'm going to redraw this circuit and I'll draw it something like this. So you have got point A and now you have got inductor, and because current is increasing, then it would actually try to decrease it, something like this, right? Then again we have got a battery as they have shown in the figure. So a battery like this, then a resistance, and then point B. Point B, point A, this is actually L di by dt, this is 5 volt, this is 2 ohm, right? So what is L di by dt? First of all, induced EMF L di by dt, L was given as dosto, L was given as 1. So 1 times di by dt, that is also 1. So that is nothing but 1 volt, right? So this whole thing is actually nothing but 1 volt. And as you are moving from one A point, so we'll write A minus 1 volt minus 5 volt minus 4 volt equals to VB. So VA minus VB would be 10 volt. Please check every calculation. If you have any doubt, please write down in the comment section. Third one is your homework, right? Find out the answer, write down in the comment section. Hopefully this will help. Now after this, we are going to actually talk about before moving to actually mutual inductance, let's also discuss the combination of inductors. Well, combination of inductors are quite easy to understand. There are mainly two types of combination, as we have studied in other cases also. Let's suppose we have got L1, L2, L1, L2 and L3. And let's suppose the total potential between these two is some V. We have connected with a battery. I am not explaining that. And some current I is flowing. And across this one the potential is V1, across this one potential is V2, across this one is potential is V3. So we would know that V is equals to V1 plus V2 plus V3. That would mean that instead of V I can actually write L equivalent di by dt is equals to L1 di1 by dt plus L2 di2 by dt. Sorry, by the way, current is same, so I don't have to actually write di1 something like that. So this is nothing but this is di by dt plus L2 di by dt and plus L3 di by dt. Di by dt can be cancelled out and you are going to get the formula of L equivalent, that is L1 plus L2 plus L3. That's how easy it is. And similarly, now if you are going to talk about parallel combination, in parallel combination the formula will be 1 upon L equivalent equals to 1 upon L1 plus 1 upon L2 plus 1 upon L3. Right? In this case, the only difference is now you will divide the current I equals to I1 plus I2 plus I3 and then you will differentiate it. So no worries over there also. Right? So hopefully everything is clear of in combination of inductors also. It's a very easy concept to understand. See, after this, we have got a topic which is actually what we can say is it is actually RL DC circuit. Now again you might say that, sir, in NEET whether we are going to talk about RL DC circuit or not, we'll quickly finish it. I'll just ask you to remember the formula and some of the basic things. That's it, right? We are not going to talk about it in great detail, right? So let's quickly start this topic as well. So now in RL DC circuit, first let's draw a circuit. Let's suppose that we have got an AC source over here. And for this, let's draw a circuit like this. Let's suppose we have got resistance and an inductor over here, and this is a terminal, and another point is actually connected with battery, and this is actually your normal DC battery. Now only thing to see over here is that we are actually leaving these two terminals right now open. so that we can actually connect them according to our convenience, right? So we have, first of all, we have got a battery over here which has got EMF E, potential difference E, resistance R, inductor L. What we want to learn in this particular topic is how does current behave when there is an inductor in a circuit, and what this or RL DC circuit is. Having said that, this is not in your directly not in your course, but still it's good to have some information. And let's suppose that we have got another part of circuit over here, something like this. So basically what we are trying to say is that first of all, this is A, B and C. So first we'll connect points A and B. So when we'll connect point A and B, current will start to flow through this battery, right? And now we'll talk about how does current actually starts to flow. So I'll just make a copy of this diagram so that I don't have to make it all over again. So the first part is when we connect A with B, and under this we are going to talk about actually growth of current. How does the current grows? Growth of current. Now please understand, we all know that inductor, what is the job of inductor? Inductor's job is to resist change in current. Now after some time, current will get steady. There will be a steady current flowing into this circuit, and let's suppose that steady current is actually E by R. That current is E by R, or you can also call this as maximum current. Current will not grow after this value. This is E by R, right? So this E by R current is the steady current, and at that point this inductor will just behave like a clean wire. This much we know, right? But from 0 ampere to this maximum value, current doesn't just grow instantly. It grows gradually. And this is because of inductor. So inductor actually slows down this process by a bit, right? So how this will all work? Let's formulate an equation, and I'll be quick. You don't have to. If you are preparing for NEET 2025, this derivation is not like a matter of what we can say. It's not like extremely important for you, or it's going to be asked in NEET 2025. But if you'll able to understand it, good for you. So the thing is, right now what I'll ask you to do is just write an KVL equation over here. So if I'll write a KVL equation, I'll write that E minus IR. Now this I is current at any time t, random time. IR minus L di by dt equals to 0, your normal KVL equation, right? Now the next step is going to be something like E minus IR equals to L di by dt. So of course now all of these types of derivations require some sort of your knowledge of integration, some sort of knowledge of how to integrate by separating the variables, all of these things, okay? So but still I'll explain it to you. What we can actually do is we can actually transpose, we can make them make the variables to move to one side. Let's suppose we'll write di over here, and in the denominator of di, let's write it as E minus IR equals to, I've got dt and I've got L. So I've got 1 upon L times dt. And now let's integrate it from time 0 to t, and when time was 0, there was no current. When we just connected A and B, at that point there was no current. And then after time t, let's suppose current is I. So we want to have a general equation, right? We are not talking about two specific cases. We are talking about a general equation. So this is your this is an equation when we'll actually integrate it. Fine. After this, I want you to actually look here, and we are going to use a formula of integration which looks something like this. I'll write it over here. The formula is integration of 1 upon ax plus b with respect to x. Integration of this comes out to be 1 upon a natural log mod of ax plus b. Fine, if you don't know it, no problem. Right now you can learn it, right? Although integration, you must learn these basic integration. So 1 upon ax plus b, right now we are trying to integrate with respect to current I. So my variable is actually current, right? So this is going to be that ax. So if I'll integrate it, I'll get something like this. So this I'll get minus 1 upon r into the in front of it. So minus 1 upon r natural log, and then you can write mod, but still if you don't want to write it, no worries. So you'll write e minus ir, and then minus lower limit. So minus natural log e, instead of I have substituted 0, so that is, and now again I'll again rewrite it something like this, divided by e. Hopefully you have got it. Equals to integration of 1 with respect to t would be t, so it would be t divided by L. Next step could be natural log e minus ir divided by e equals to, I can transpose this minus r to the other side, so this will become minus r by L into t. If I'll actually do one thing, if I'll take the anti-log both the sides, so I'll get e minus ir upon e equals to e to the power of minus t upon, or right now let me just write it as minus r t by L, right? See, now in this step we are going to write something like, we are going to write, let's do one thing, let's rewrite it as e minus ir equals to e times e to the power of RT by L. Hopefully everything is clear till this point, right? Hopefully everything is clear till this point. Next step is going to be IR equals to, I'll take E as common, and this would be 1 minus e to the power minus RT by L. Again and again I am saying, even if you are not catching up with me along the derivation, no worries, final result will be very, very important. So you must remember that, right? So now let's divide that r to the other side. So this will become E equals to E by R. E by R is nothing but, okay, I'll write one more step, 1 minus e to the power. Now please see here, I am going to do something over here. This thing can be written as minus t upon tau. We have written something as tau. You know what that tau is. Tau is actually L by R. And finally the final equation will be, I'll write the final equation somewhere over here. The final equation is going to be I equals to I naught 1 minus e to the power minus t upon tau, right? And this is the equation for growth of current. So you must remember this. And in this equation we can write that tau is actually is known as a time constant, whose value is nothing but दोस्तों L by R. It is L by R. All right, it is L by R. If someone asks you what is going to be the unit of this tau, so unit of this tau is going to be second. Not that I can actually so quickly I can derive that L upon R is second, but I know one thing, whatever is in the power of E, e to the power is anything, that thing is dimensionless. So I know that I have got time over here, so this tau must be should be also in seconds, so that this whole thing becomes dimensionless. This is one point which will be useful for you in units and dimensions also. So please note it, or please revise it if you have forgotten it. Right, so I equals to I naught is the maximum current that we were talking about, E by R, right? 1 minus e to the power minus t by tau. So this is the equation. And now if we'll see this equation, if I'll write this equation again, I equals to I naught times 1 minus e to the power minus t upon tau. By the way, that tau is L by R, and in a complex circuit that tau will change, but we'll never see a complex question from this particular topic in NEET. If we are seeing this equation, let's talk about, this is current at any time t. But let's suppose we are talking about just after switching the just after closing the switch, just after closing switch. That means T is equals to 0, right? So if T is equals to 0, current will be I equals to I naught 1 minus e to the power of 0. Anything to the power of 0 is 1, and if this thing is 1, 1 minus 1 will be 0. That means current will be 0, which we were talking about, right? We said that just after you are going to close the switch, current will be 0. We knew that. And the another extreme will be that is the steady state. Steady state basically means T is actually infinite. So if T is going to be infinite, this e to the power of minus infinity is going to be 0 and I will be actually I naught. So the graph of this particular thing will look something like this. The growth of current will be looking somewhat like this. We have got time over here, you have got current over here. Let's suppose that the maximum value of current is this, right? So the growth of the current will be somewhat like this. Hopefully you're getting it, right? Now there is also a significance of a time constant. That means let's suppose we are talking about after one time constant. After one time constant. What does this mean? That tau is actually equals to, let's suppose tau, sorry, not tau, but after t equals to tau, that is one time constant, that would be correct. So if t equals to tau, this would basically mean e equals to e naught 1 minus e to the power of minus 1, right? So e to the power of minus 1 upon e is around 0.37. So 1 minus 0.37 is going to be I equals to 0.63 times of I naught. That means what you can now say is that after one time constant, current achieves it 63% of its maximum value, right? So you might say that somewhere over here. This is one time constant, T equals to, you can also write it as L by R. See, the current is going to be 0.63 times of I naught, where this is I naught. All right, so that was the about growth of current. Hopefully everything is clear. Now let's talk about decay of current. So similarly, if now we are going to talk about this case. Now let's say we are connecting, instead of connecting these 2 points, we are connecting A and C. So that will be called as decay of current. Now I will not derive it because I mean this derivation is actually quite simple. So if you are going to again apply the KVL, you will get something like IR is equals to minus L di by dt, and differentiating this equation you will get I equals to I naught e to the power of minus t by tau. So do remember this equation as well. You are going to need it, and simply what we are going to say is that at t equals to 0, assume that there is an air gap. The inductor is actually, it is actually possible for an inductor to block that current. So at t equals to 0, assume an air gap across an inductor, and at t equals to infinity, this is part B, at t equals to infinity, assume it as a clean wire, right? So with this, what you can now do is, we can look for one example for let's say calculate the current which given in the battery is following just after closing the switch. So just after closing the switch means that there is nothing, there will be no current over here. So for part A, the R equivalent would be 2 and 3 just, so that would be 5, and current would be 10 divided by 5, 10 divided by 5, that means 2 ampere, right? So 2 ampere of current should come from the battery, and after a long time, after some time after it, then we'll say that okay, now inductor will, there will be a clean wire over here. So now you can find out again R equivalent, parallel combination 6 and 3, then series, and then find it out. Okay, so please do it, very easy, not so difficult. Let's move on. Next question is, a coil of 10 Henry inductance and 5 ohm resistance is connected to 5 volt battery in series. The current in ampere in circuit 2 seconds after the switch is on. Alright. So we know that current is actually I equals to I naught. I equals to I naught 1 minus e to the power of minus t upon L by R. So L and R is over here. Now I naught is nothing but E by R. So E is 5 volt, R is given as 5 ohm times 1 minus e to the power t is given as 2 seconds. Hopefully everything is clear. T is given as 2 seconds. Resistance was given as 5 ohm and inductor was given as 10. So again this will become 1. So this is also 1. So I is coming out to be 1 minus e to the power of minus 1. 1 minus e to the power of minus 1 means option B. Hopefully everything is clear. Quickly, if you have any doubt, let me know in the comment section. Okay. Now the next topic is going to be mutual inductance. So we have not skipped RLDC circuit. We have covered it, but mutual inductance is actually important. In mutual inductance, what we are going to say is, let's suppose we have got, instead of now one coil, we have got, let's say we have got 2 coils. Let's say this is a primary coil. And we have got over here as another coil, which we are going to call as a secondary coil. So let's say the current flowing in the primary coil is I1. The number of turns in this one is N1. The number of turns in this one is N2, right? And there can be current, there can be current of secondary coil of its own, but right now we are not talking about it. This is secondary coil. This one is primary coil. See, the concept is very simple. We'll simply say that the flux linkage in the secondary coil will be directly proportional to the current flowing through the primary coil. Why is that? Because if current will flow through the primary coil, it will produce a magnetic field. That magnetic field will get, that magnetic field, we are going to say there is a magnetic field linkage of primary coil with the secondary coil. So there is flux, and if I change I1, magnetic field will change and flux will change. So flux linkage with 2 is directly proportional to I1. The proportionality constant here is going to be called as the mutual inductance. So that means M will be actually equals to phi 2 divided by I1, and M is the coefficient of mutual inductance. Again same thing, same unit is going to be Henry. This is also a scalar quantity, that means scalar as well as always positive, right? And if someone now tells you to find out the induced EMF, you can find it out by minus M di by dt. Is that clear? Minus M di by dt, you can also write it like this. So this is not very difficult. Or what we are going to now focus on is, we'll find out the mutual inductance due to a solenoid, right? Due to 2 coaxial solenoids. So mutual inductance due to coaxial solenoids. Now in this, see, what we are going to say is, let's suppose we have got solenoid like this. all right, and this, let's suppose it has got some turns. Let's say it has got N1 turns, and I am talking about a general case so that we can, after this we can derive all the specific cases. It has got some length L1, total length is L1, current that is flowing in this solenoid is, let's say, I1, all right. This area of cross section is A1, all right. Next, let's suppose we have got another solenoid which is inside of it, all right. So we have got another solenoid which is inside of it, something like this. Which has got turns N2, something like this, right? Hopefully everything is clear. We have got two coaxial solenoids. Length of this solenoid is, let's say, it is L2. Number of total turns is, let's suppose, N2. Total number of turns in the primary coil is N1. If you have not written it yet, total number of primary coils is N1. Area of cross section of the smaller coil is A2. Hopefully everything is clear, right? Now what I'll say is, I've specifically told you that current is flowing in the bigger solenoid. See, any case can be made from here. So now we'll simply say one thing. Okay, so if we want to find out the flux through this surface, we want to know the flux through this surface, so we'll write something like this, that flux linkage with the secondary coil is actually equals to, and right now I am talking about the total flux, the total flux linkage with the secondary coil is actually equals to N2, total number of turns, multiplied by magnetic field produced by solenoid 1, because that is who is creating the magnetic field, multiplied by area, and area is of the secondary coil, because flux is getting linkage with only this part. Hopefully everything is clear. Or you can do, you can actually change it. You can also say, okay sir, now I am saying that current is flowing in the inner coil, and then I am finding out the magnetic flux in the first one. That is also good, no problem with that as well, right? So this will be something like, hopefully everything is clear. So this will be phi 2 total is equals to N2, and B2 is going to be mu naught into total number of turns N1 divided by L1 into I1 into area A2. You can simply write it as A2, nothing to worry about, right? So phi 2 divided by I1 will be actually your mutual inductance, and that will be nothing but, if you closely see, it will be mu naught N1 N2 upon length L1 times area A2. Have a look. Although generally when you'll have a numerical on these things, generally you'll be able to solve it using this thing only, right? But still have a look at this. Now moving on, we have got one more thing that is known as coupling factor related with mutual inductance. Why we are calling about something as coupling factor? Because see, if you'll closely see, what is the difference between these two coils and these two coils. What is the difference between? The difference is that we can actually sense that, okay, the magnetic flux that is linking with the secondary coil over here is not maximum, whereas in this particular thing maximum magnetic flux is getting linked. That is, no magnetic field lines are getting waste, you can also call it like this, right? So there is a term which is actually called as coupling factor, which is actually known as coupling factor. So coupling factor basically tells you the design or the fashion in which the two coils are kept, right? For example, first of all, let me write it down for you. You don't need to go learn for derivation. I don't think there is derivation for this thing in any book. So and you don't need it. What coupling factor basically means, mutual inductance between two coils can be written as K times under root L1 L2, right? So now it will depend on K. So K is your coupling factor. It will depend on K, whether what will be the value of mutual inductance. So for this particular case, that was the coaxial, K was maximum. So maximum value of K is actually +1. And what do we mean by maximum coupling factor? That means maximum number of flux are getting linked. Over here we will say some of the magnetic field lines might not get linked, because and if you are going to increase the distance between them, K will further decrease, right? So K basically tells you the coupling fashion between two coils. So let's quickly draw some things. Let's suppose that you have got coaxial. You have got coaxial coupling. Let's say this is primary coil, and on the same core you are winding secondary coil also. So this case will have maximum coupling, that is coaxial, and maximum coupling basically means K max is equals to 1. And when it will be minimum? So minimum case is going to be something like this. Let's suppose you have got one coil like this, and the another coil is at the 90, is at perpendicular. That means axis of both of these things are at perpendicular angle, are perpendicular to each other, sorry, right? Something like this, because magnetic field lines are going to be produced in this way and there will be no magnetic flux. So this is for a minimum coupling, that is 0. No magnetic flux is getting linked. So generally K is between 1 and 0. So hopefully you have got it. Other than that, if you are going to actually increase the separation between the two coils, K will actually decrease. Separation between two coils, right? So K will decrease. So remember this thing as well, right? So my dear friends, hopefully you have understood how we are writing coupling factor. This is actually important because you are going to actually use mutual inductance when we are going to talk about transformer. So this is actually very important for us, right? Now before talking about transformer, let's talk AC generator. AC generator is going to play the basis or the basis concept of for alternating current, right? Very easy. You don't have to go for its working, you don't have to go for how it works for individual parts. You must understand the concept behind it. The concept is simple, that if you have got a if you have got a moving armature over here in the magnetic field, it will lead to change in flux. If there is change in flux, there will be an induced EMF in this armature, right? So we have got different parts over here. We have got this coil, which is actually nothing but a rectangular armature, right? We have got field magnets over here to create a strong magnetic field. We have got an axle over here. So through axle, basically a generator, what does a generator does? A generator basically converts mechanical energy to electrical energy. So through that axle, we are going to actually through that axle we'll try to rotate this this armature, and how from where that mechanical energy will be drawn, that is a separate issue. You can actually use a hydro power plant, a coal power plant, a nuclear fission power plant, anything. That's what the mechanical energy we are going to use, right? And using that, this is going to rotate at any given point. Let's suppose at any given point flux will be BA cos theta. BA cos theta. Theta can be written as omega t. Let's suppose it is rotating with angular velocity omega. By the way, these slip rings are used to actually derive the current from this rotatory body to your circuit. So this is actually a type of a touching point from your circuit to these to this rotatory shaft, right? If we will not use these, how you are going to actually get the alternating current? Because after every half cycle, current's directions are going to change, right? By the way, touching points are those carbon brushes. These are basically to derive the current from the rotatory shaft to your circuit. So B can be written something like this. Now if we are going to actually change this, that is d phi by dt, this will lead to minus B A omega cos omega t. And by the way, if we want to write for the total flux, we will have to multiply it with the total number of turns, because armature basically means this is the woundings of, we have wounded many wires. So multiplied by a total number of turns over here. And also if we talk about induced EMF, this is going to be minus, so this will be something like NBA omega cos omega t. This is what it's going to be useful for you, right? So in this particular thing, if you can see, we have got a function. I always explain you in this way. We have got a function cos omega t. This has got maximum value as minimum value as -1, maximum value as +1, right? That means this E will have maximum value as some E naught, that is going to be NBA omega, which we are going to now call it as plus E naught, and similarly minus E naught. So the minus part of this same. So this is the maximum EMF. So now EMF can be written as E naught sine, sorry, if this has to be sine, na? My bad, you must have, this is sine. So this is going to be E naught sine omega t. So now please see here, you don't have to draw all the graphs, although you can see it in old NCERT. We had the graph of how the flux changes, how the armature moves, how flux changes, and how induced EMF is generated, right? We don't have to worry about all of those things. You can simply see it. But if let's suppose we want to know that where we have got maximum EMF. So we have got maximum EMF for at least for this particular thing, for this particular equation, at when theta is actually pi by 2, and at pi by 2 flux is actually 0. All of these things, right? So there is nothing to worry about AC generator. This is going to be the main. From here we are going to start our alternating current chapter, right? Before moving on, now let's actually also cover transformer. Not very difficult topic. Sometimes transformer is also completed in, sometimes we study transformer in a alternating current also, but we are covering it in electromagnetic induction. See, what do we use, why transformers are used? Transformers are used to actually change voltage slash, if you are going to change voltage, it will automatically change current, but generally we say that we change voltage, and it is changed in two types. First is, we have got step up transformer, and we have got step down transformer. Let's also discuss why there is a need of changing potential. Why do we do that? Just now we saw that how electricity is generated through AC generator. I have not explained all of those things because I think in 10th class also you must have gone through AC generator. Although I also know that for many years AC generator has been deleted, but for NEET you are mainly concerned with the concepts that we have already done in Faraday's and Lenz's law. Then you are concerned with the numerical part. So both the things are covered. Now you don't need to actually write down the construction working of any, we don't have to write essays. Now for transformer, the need is that after the electricity is generated at the power plant, it needs to be actually transported to the residential areas or to any areas where electricity is needed. During that transportation, there will be high energy losses if we have got high current, right? Because we know that heat is directly proportional to the square of current from Joule's law. So we want that current should be very low. That's why I said that just not talk about change in voltage. Our main purpose is also, if you will change voltage, current will also change. So at the power plant, we actually step up the voltage, and those transformers are known as step up transformers. That means we actually increase the voltage, and we decrease current so that we can decrease energy loss, right? And we increase it to like high values of 11 kV lines and in order of 11,000 volts, something like that, right? And then after that electricity reaches to your city, it is being dropped down. That means the voltage is being dropped down at multiple levels. First it reaches to the substation, it is dropped down. So a particular locality has one or two substation, it will get dropped down by a certain value. Then that potential, that current will reach to your colony or your or whatever your campus, right? In those you have got transformers that you see, and obviously they don't look something like that because they have got what we can say an iron shielding over there. Then that transformer which is in your colony, it finally steps down it to 220 volt that we use at our homes, right? But finally coming to this thing, we have understood why we use transformer, why we call them a step up and step down. Let's suppose we have got an AC current over here, right? If you have got an AC current over here, what we are going to do is we are going to actually, first of all, we have got a core over here. In this core, we have actually wounded two coils. We have wounded primary coil. So this is a primary coil, and on the same core we have also binded the secondary coil. So from the primary coil you have got your input alternating voltage, right? And this is an iron core, and why it is looking like sheets, because that's what it is. These are the laminated sheets. These are the laminated sheets. So we could have actually made a big block, and by the way, this is actually iron core. So all of these sheets are made up of soft iron core. Why we use soft iron core? We have discussed this multiple times during the previous chapters. We use soft iron core because it is easy for handle the magnetism of these bodies, right? The next thing is, why do we use laminated sheets? We could have used a one single big unit of soft iron block. In that case, there is something that is called as eddy current. I've got notes for you, so don't worry about it. But eddy currents are nothing but your normal induced current. These induced currents are produced in the metallic surfaces when magnetic fields are changing, right? So to minimize that loss, because if induced current is getting produced, there will be some loss. Some will have the energy. If there is some electrical energy, there will be certain losses. So that's why we actually make this iron core as laminated sheets. And why do we are, and the purpose of wounding these primary and secondary coil close to each other is so that there is no flux leakage, so that the coupling factor can be maximum. Generally, they are generally wound over a single, what we can say, a single core, right? So this is the case. Now again, we know few things. Let's suppose that the primary coil has number of turns as NP, secondary coil has number of turns NS, right? Now we can say that if I'll say to you that induced EMF in the secondary coil will be actually equals to minus times of NS d phi by dt and d phi s by dt, the change in flux in that primary, in that coil, divided by dt. Hopefully everything is clear. This is nothing but Faraday's law. Similarly, EP can be actually written as minus NP d phi p by dt. Now because we are saying that there is no flux leakage, that means rate of change in flux is also going to be same. So instead of writing ds, we can simply write it as d phi by dt. So if I'll take a ratio of them, es divided by ep, what I'm going to get is I'm going to get ns divided by np. See, I'm not going to call these as derivations. These are very simple thing, but questions usually come from these topics, so please note all of those things. So wherever there is an assumption, I'm telling you, so here it's not like an assumption, but we are actually saying that we could actually write something like this because there is no flux leakage. No flux leakage. This is possible, right? What is not possible is that if we are talking about an ideal transformer, ideal transformer basically means that you are actually neglecting all the losses. And if you are neglecting all the other losses, what does it mean? It means that whatever input power you are giving to the primary coil, that is exactly equal to the output power from the secondary coil. And input power basically means Vp, Ip, or because I should use same notation, Ep, Ip equals to Es, Is. So just now we have written Ep upon Es would be Np upon Ns. By the way, Ep upon Es can be also written as Is upon Ip equals to Np upon Ns. So now everything is clear. We can now, this is an assumption that we are saying that basically we are saying from this point that efficiency, which is actually 100% in this case, this is an ideal phenomena. Other than that, realistically efficiency is actually output power divided by input power times 100, right? So if you want to step up, if you want the voltage to step up, so what you need to do is, if you want ES to be greater, then increase the number of turns in the secondary coil, and that will decrease IS. That's what we have talked about, right? So that will decrease the current through the secondary coil. So this is the ideal transformer case. And you can also now make some questions, like for example, as let's say we are talking about a step-up transformer. So which coil should have a thicker wires? Just a hypothetical question. So if it is a step-up transformer, that means secondary coil will have greater voltage and lesser current. So this will have lesser voltage, greater current. So this one should have thicker wires, so that it can withstand the heat produced by larger current, right? So now let's talk about some other losses. So losses can be copper loss. Copper loss is basically the wires that that we were using of that coil. If that wire has got some adulteration, there's some mixing up of metals, then the resistance will increase and there will be some losses, right, due to heating effect of electric current. To minimize these losses, high current coil always made with thick wire, and for removal of produced heat, circulation of mineral oil should be used. So this is actually very important, that in transformers, because transformers are used continuously, We never actually give rest to a certain machines. Transformer is actually one of them. So we use transformers. Actually, we try to use transformer for 24/7, 365 days. Although in India they get ample of rest, but still lots of heat will be produced. So to actually cool that, we use liquid oils, right? And you must have heard this liquid cooling, oil cooling in automobiles also. So liquid oil is actually used to cool them. Another type of loss is flux leakage loss, already discussed it. The losses occurs in between the coils of the shell part due to air gap between the coils, right? To minimize these losses, both coils are tightly wound over a common soft iron core. High magnetic permeability, so a path of magnetic field lines formed itself within. See, whatever I have told you, this is just written in language, right? Then last part was, there is also hysteresis loss. Hysteresis loss, because you are talking about alternating current, so again and again you are going to magnetize it, then demagnetize it. For half cycle it will get magnetized, for another half cycle it will get demagnetized. That's why we are using soft iron core. If we'll use some material like steel, it will get lots of energy, lots of magnetic field to get demagnetized, because it has got higher retentivity and cohesivity, right? So that's what we have written over here. Soft iron should be used. And the last loss, that is eddy current losses. Eddy current losses I have already explained you. Eddy current basically gets built up on the metal surfaces of metal blocks when there is changing magnetic field, right? Hopefully everything is clear with transformers also. Now friends, after this we have completed electromagnetic induction. Take electromagnetic induction and alternating current as a complete unit, right? That will actually benefit you a lot. Next class will be of alternating current. So keep studying. If you have any doubt, let me know in the comment section. Till then, take care. Thanks so much. Bye bye.